Hello, welcome to this lesson in engineering circuit analysis op-amps. We're going to finally in this section derive, or I should say, talk about the common mode and the differential mode signals, which is leading up to our derivation of the common mode rejection ratio. Now in the last section I taught you what the common mode rejection ratio basically was from a top level point of view. And so go back and look at that if you haven't already done so. But if you remember, the punchline at the end of that was that there's really a gain that's associated with the difference of those signals. We call that A sub D. And there's a totally separate gain for the common mode signals, A sub C. And the ratio of those is what we call the common mode rejection ratio, right? So we want that difference, AD, that difference gain to be very high, and we want that common mode gain to be very low because we want to reject the common mode signals, as we've talked about over and over again. So what we're going to do now is embark down that journey. Now the good news is that none of this math is calculus or advanced, quantum mechanics. It's not difficult mathematically, but it is easy to get confused. Even when I first learned this, it was a little confusing. So what I'm going to do is take it step by step and really show you what you're probably going to read in your book as a complicated derivation, but we're going to make it simple. And it's actually kind of interesting the way we do. Now, the first thing you have to do is in your mind, to derive the common mode rejection ratio, we need to write our input signals V1 and V2, which are pairs of signals. We're talking about pairs of signals now. We need to write those in terms of a common mode component of that pair of signals and a differential mode component. Now, this is kind of foreign stuff because up till now you really haven't looked at components of signals and components of pairs of signals. But basically, the punchline is any pair of signals. Notice these amplifiers have pairs of inputs. They're difference amplifiers, right? Any pair of inputs can be written in terms of its common mode component and its difference mode component, right? And what we're going to show through all the math is that when you do that, when you write the pair of signals in terms of a common mode and a difference mode component, what we're going to show is that the gain associated with that common mode should be really low, and the gain associated with that differential mode should be very high, which is what I already told you was going to happen anyway. But still, the concept of this components thing is a little bit weird at first. So I'm going to draw an analogy to you, for you. Remember a long time ago, back when you were taking baby steps in math, you learned about the concept of a vector, right? So we have X and we have Y. And you learned that this little arrow is this thing called a vector. It could be the wind speed or whatever, but it's pointing this direction and it has a certain length associated with it. Right? And you were taught that you can use vectors for all kinds of things, right? You can use it to describe the magnetic field, which direction, the strength, the electric field, all kinds of things, wind speed, velocity, all kinds of useful things. And you start learning about the concept of a vector. Then you dive into the math behind vectors a little bit more and you realize that every single vector that you can write by definition can be broken into components, right? And you learned that the tip of this vector can be, you can look at the projection here, and you could call this V sub x if this vector is called V, right? But this is a scalar component in the x direction, and it looks like I'm going to make a mess here going through my little label, but anyway, over here you have V sub y, right? And at first when you learn that, you don't see the usefulness of it. You don't understand, how incredibly useful that is until you start looking at problems and realizing that this vector V can be written, right, basically as the x component, Vx, we call it in the I direction, plus Vy in the j direction, right? So you can write the vector in terms of an x component in the x direction plus a y component in the y direction. And still, even at first, you may not really understand exactly when you first learned it why that was so powerful. But the reason it was so powerful is because I can take any vector pointing in any direction I want, let's say a magnetic field strength pointing this angle or whatever, this strength, right? And then instead of having to deal with that all at once, I can break it up into components. Then I can only look at how the magnetic field or whatever it is pointing in the x direction. I can deal with my equations only in the x direction, because that vector can be broken into basically two different smaller vectors, really an x vector and a y vector, which sum together to be the real vector. So I guess I'm just trying to draw an analogy because the same thing is going to happen here. We can take any vector, we can break it into components to make it easier to operate on each direction. And we're going to do the same thing with common mode and differential mode. Any pair of signals, V1 and V2, can be broken into components. One component is called the differential mode component. One component is called the common